It is now 12:01 p.m. Central Time, and I am your host, Dr. Matthew Richardson, and welcome to another day of CosmoQuest Astro Office Hours. All right, so guys, we're actually going to pick up where we left off during the last stream. That is talking about black holes. But before we jump into all the fun, let me go ahead and first verify that I'm actually streaming. So let's see. Opening up Chrome. Let's see what we got here. Oh, oops, wrong one. Let's see. It's still showing that I'm offline. No. I'm streaming based off of that little bit of footage I saw. Let's do this. Let's reload the page and let's see if it gives me access to the chat. Okay, that didn't do it. So let's, as normal, exit Chrome completely. Reopen Chrome. Navigate back to Twitch. Go to the CosmoQuest channel, which is now showing a red dot, meaning that someone's live. And I thought I saw myself for a brief moment a few minutes ago, or seconds ago. And yes, I am live. Let me go ahead and pop out the chat so we can go ahead and get this show on the road. Oh, yes, black holes. Can we slingshot around it in time travel? Time travel. So much fun. Hey, Side MT. All right, let me quickly make a quick, I don't want to say shout out. Let me say hi to everybody. Let me see who's all here according to what Twitch is going to show me. Let's see. Still loading. All right. Now, I'm not too sure if you guys are actually here, but hey, Big J. Hey, Electrical Skateboard. Hey, Kate Borut. You're a new person here. Welcome to today's stream. Hey, Larry. Hey, Michael T. Mayer. Hi, Peter. Hi, Tchaikovsky. And hi, WJM Tech. Welcome, guys. I'm pretty sure that it missed some people, like Side MT and Jetlander. Hey, guys, welcome. All right. So today we're not exactly going to be talking about what we talked about in the last stream, which was what was that? We were talking about the Schwarzschild radius. Someone told me that I was saying it incorrectly. Hopefully that's the correct pronunciation. Let's see. And we start getting into talking about black hole density and stuff like that. Today, we're going to be talking about another topic related to black holes. Hey, Keeper of Maps. And so we are talking about spaghettification. What is this whole thing of spaghettification? So let's go ahead and get into it. So, my understanding of it is that when you are in the presence of let's say for the most part, an extreme gravitational gradient, one's body can be stretched in such a way that you essentially will become like spaghetti, which is kind of scary. Yep, that's it, Michael T. Mayer. That's it, DG over DR. And so we actually talked about this, right? So what Michael's getting at here is that tidal forces. And so we actually talked about tidal forces in one of the previous streams. So I'm actually going to just be like copying and pasting some of the derivation for the tidal force equation. Well, not tidal force equation, but for differential acceleration due to tidal force. Hey, Guido. It's funny that you're cooking because we're going to be cooking today. We're talking about spaghettification. We're cooking science style. Astronomy. Yeah, delta G over delta R, Larry. Alright. So, let me go ahead and do a quick modification. Yes, G is gravity, but the R represents the length over which the gravity is acting, in this case. Alright. Let's see. I wanted to do something just now. I want to open up one of the past streams. Hey, Susie. So let me go ahead and, you guys can't see me doing this right now, but I'm basically opening up the folder that holds all of the PDFs and code that was generated for previous streams. And I know that in one of these folders we did talk about tidal forces. So let me do that really fast. Let's see, Planetary Science Institute, CosmoQuest, Astro Office Hours, and this is probably a recent discussion. Let's check number 32. Nope, that's moon distance. 31, diameter of the Earth. 33, physics radioactivity. That's not it. Tides. There we go. All right. This is the one I'm looking for. And so in the tides PDF, I do know that we end up doing the derivation. Oh no, my text shot quit. That's weird. Let's reopen it. Luckily, you guys did not see my tech shop program, just die on me there. All right, let's try to reopen tides. There we go. All right, so let me scroll through it and let me extract the information that's important to us. Interesting. Okay. All right. So we actually do calculate the tidal force, which is cool. We can still do this. All right. But I'm still gonna make a slight modification to it. So I'm gonna quickly copy and paste. Let's see, where is it? Tidal force, proportionality, blah blah blah. Where are you? Tidal force comparison. There we go. So we're gonna copy this section. And you guys will see me pasting it in just a second. Wait, let me make this font a little bit bigger. And let's minimize this, and let's make this font also a little bit bigger. Okay, hopefully that's better, guys. All right. So we're gonna go to the bottom of this. I'm gonna copy and paste what I took from one of the previous streams where we calculated the tidal force. Let's go ahead and blow this up. Or what I mean by that is, let's go ahead and tech it. And so this is the equation we can use for the differential force across a body. And so due to gradient in force. Okay, so what we want to do with this, to be able to make it applicable to, let's say, a black hole, is our r for this particular equation, well, not so much delta r, but the r cubed in the denominator on the right-hand side of the equation. This r represents, in this case, would be representative of our Schwarzschild radius, excuse me. Whereas the delta r would represent smaller changes in r, and would be the gravitational, or the differential force across. In this case, we're going to use like a human, for example, that's in the presence of a black hole. So let's make sure I'm not missing any of the topics or conversations here. Okay, I'm quickly looking at a comment that Larry stated earlier. Not the radius of the center of gravity. So yeah, this is going to be a differential. It's going to be a differential. Basically, it's going to be the change in gravity over some change in length. I like that article, Big J. I think there's some validity to that. I'm pretty sure that eating pizza will definitely get the day off right for everyone. All right. So let's go ahead and we're gonna, of course, modify this equation to take into consideration that we are talking about the tidal force, or tidal force due to black hole. And I'm going to get rid of this whole proportionality stuff. All right. And so our r cubed is now going to be an r cubed. The r is now going to be replaced by the equation we derived for the Schwarzschild radius. So I'm going to scroll up top. Just going to do a simple copy and paste. Or better yet, let's copy and paste this first. And now let's go ahead and make the substitution for the Schwarzschild radius. And again, I also have another scene that I can like load up where we're going to be doing everything using in C++ to do our calculations. All right, so let's do this. Left, right. Throw that in there and let's see what we get. Oops. A little bit of formatting problem there. All right, that should be better. And so this is the equation we're basically going to get for the differential force, or the tidal force across anything, actually, any massive object, any object with mass that is close to the event horizon of a black hole. So let's go ahead and simplify this equation. And we should get, and guys, please, please do check my my algebra. Oh my God! Thank you, Michael, for saving the last stream there. But check my algebra, guys, because there are times it skips at times. Like, it's weird. All right, so I'm gonna work through this slowly, and guys, make sure I'm doing this right. All right, so the negative sign stays. I basically have a 2 to the first power over 2 cubed which gives me a 2 squared in the denominator, which is basically 4. Cool. So I'm going to get rid of my 2's. Right. And I'm going to put a 4 down there. Better yet, let's leave this line and make a new line where I make my modifications. Alright. So get rid of the 2 in the numerator and put a 4 in the denominator. Alright. Again, this is going to give me a g squared in the denominator. So g squared. This will give me a capital M, where in this case the capital M corresponds to the mass of the black hole. So it's going to give me M squared. Interesting. All right. So it looks like the differential, the tidal force also goes as 1 over M squared, just like the density. All right. So so far so good. And if I'm not mistaken, this is going to give me a c to the 6th power in the numerator. I really am second guessing myself here, guys, because I made a mistake last time. All right, so let's just put a c raised to the 6th power. I think we're good here. I need to get rid of the g and the m. All right. Alright, I think this is right, which allows me now to get rid of everything else. Even the cube. Let's go ahead and typeset this. And I believe this should be our final equation for the tidal force due to a black hole when you're nearby the event horizon. Yeah. Because the r that we're using is the Schwarzschild radius. All right, let's make sure. I'm just gonna look over it again because, yeah, I just want to make sure the algebra is correct. Let's see. All right, 2's are good. The g looks good. The capital M looks good. The lowercase m looks good. Also, yeah, guys, the lowercase m corresponds to the mass of the object that's undergoing the tidal force. And then the C. I think this is good, guys. If there's a problem, let me know. Michael is right. Oh, it's much easier to read when I'm editing C++. Are you familiar with LaTeX, Michael? I fear no math. Yeah, I fear math. Okay, you're a programmer. That makes sense. That makes sense. Also, guys, make sure that I'm using the correct the most efficient methods also when I'm programming too. Because you've never used LaTeX. Yeah, honestly I didn't start using any of this stuff until to grad school. I mean, I used a little bit of I started off using IDL, which from my understanding was made by astronomers for astronomers. And then someone told me to wise up and move on to the bigger and better C and C++. And I haven't went to any other program since, or programming language since. Let's see. So yeah, Michael's right. You don't really get spaghettification near really large black holes because of the fact that the tidal force, as we can see here, is 1 over m squared. So the larger the mass, the smaller the tidal force will be, in this case near the event horizon. Okay. Well, that's actually pretty good actually. So you are also learning how to use LaTeX as well, which is good. All right, so this is going to be our equation for our tidal force, And so I actually want to test that. So yeah, when I got into science initially, I thought it would just be me, working with math a lot with equations like day in day out, right? Then I find out that I have to write papers. It kind of messed up. I was so disillusioned when I found that out. Oh, Peter, I see that statement. I see that statement. Hey, Uncle Bill Druin. So today we're talking about the tidal force that one would experience when you are nearby the event horizon of a black hole. And as Michael already noted, which I was going to get to a little bit later, but he kind of gave ruined the surprise that and you can actually see it in the equation though, that the tidal force is proportional to 1 over m squared, capital M squared, where the capital M corresponds to the black hole mass, meaning that when you're near the event horizon for massive black holes or higher mass black holes, the tidal forces that you'd experience are going to be smaller compared to if you are near a black hole that is being generated by a much smaller mass, which is weird, right? Because it makes you think like, what if you have like I don't know, and I mean I'm not a black hole expert or anything like that, but like what if you have a mass that's like comparable to that of a human, right? But then again, I need to look at a few things. I wonder how exactly what would be the Schwarzschild radius for that mass. We could calculate that, but there were things I would have to also consider as far as like the tidal force of someone who's nearby the event horizon of a human mass, black hole. All right, let's go ahead and let's go ahead and do this. For like for a supermassive black hole, and also for a I guess like a solar mass type black hole. So this is the part of the stream where we're going to now go to C++. So let's go ahead. I'm going to slightly adjust my camera there. Let's go ahead and let's switch scenes. I currently already have it up. I think I need to still load the actual source code. This is the make file. And I generally use a make file that I wrote like a really long time ago. It seems to always work. I haven't had any problems with it, yet. And I know how to modify it if I ever do have problems. Alright, so I want to go to the source directory. Where am I at? Okay, so let's change source. We have our black hole source code there, so alright. And so, for the most part, this particular program, if you guys missed the last stream, I believe we can pass it. We pass it 2 arguments. Let me scroll up. We can pass it 2 arguments. The first argument is going to be the mass of some object, and the second argument is going to be the density of an object. And so with the first argument, the mass of an object, what it would return is the density of the corresponding black hole given that mass. For the second argument that we pass, if we pass a density, assuming this is the density of a black hole, that is, it'll return the corresponding mass of the black hole, or the mass that's encompassed within the Schwarzschild radius. Alright, so now we're going to also add on some more information here. I need to modify this particular statement, but let's see. We want to also now add on differential force, the tidal force. Yeah, let's actually. I want to modify this. I don't want to do. I don't want to do tidal force. I mean, we're still doing tidal force, but I want to. I want to instead think about the acceleration that's the differential acceleration that's happening on the person that's near the event horizon. So let's actually go back and make one little small modification. We're going to change this from differential force to a differential acceleration, which is really, it's all it is dividing both sides by the mass of the object it's experiencing the differential force or tidal force. So let's see. This is tech. I'm going to scroll down here. I'm just going to make a quick modification. And basically all I'm doing is dividing both sides by the mass of the object. So this now becomes acceleration, and the m goes away. And the negative sign can stay for now. Oh, sorry about that. So at the end of every line I put these double dashes to allow the tech software to understand that I want a new line. All right, and there we go. And so now we can go ahead and we can actually write out a function for the differential acceleration acting on a person, in this case, near, or acting on any object actually, because this is independent of the mass of the object. The differential acceleration acting on any object that's in the vicinity of the event horizon. Let's go ahead and write up the function. Let me make sure I'm looking at the comments to make sure I'm not missing anything. So yeah, the reason why I want to do acceleration is because I want to be able to compare it to the things that we know, right? For in this case, I mean, the acceleration that many of us like know really well is like the acceleration here on Earth. You can always get the forces by multiplying by your mass. And so really, the tidal force will vary from person to person, assuming that each person has different mass. But the acceleration, the differential acceleration would be constant. I think that's the way in which we should interpret this. If I'm wrong, guys, let me know. All right. So let's go ahead and calculate both. All right. So we will actually do both. We'll set up two functions actually. That's a good idea, Michael. So let's go back and let's go ahead and write up these functions. Why am I not? There we go. Let's make sure you can see what I'm seeing because I don't want to start typing in. All right. So we're going to scroll up top, and we need to now make two more functions. And I'm just going to call these functions force, and we'll understand, or let's put tidal force. It'll have its arguments. And let's put tidal acceleration. And it'll have its arguments. Let's see how many arguments should we need. We definitely need one for the mass. And that's going to be for both. We'll need to pass the mass to these two functions. Is there anything else? Let me go back to tech. So you guys can see what I'm seeing here. The speed divided is a constant, 4 is a constant, g is a constant. Delta R. We need to know exactly how tall or the height of the object. Or the length of the object. So we need that as well. So we need to pass these two functions two things. And also in the case of the differential force, we need to know the mass of the object. So let's go back. So I'm seeing 3 doubles. I'm seeing 3 doubles for the tidal force. And only 2 doubles for the tidal acceleration. Or differential acceleration. Due to tidal force. Alright. So now that we've declared our 2 functions before the main function, let's go ahead and define them after the main function. Let's go down here. And so I'm going to end up stealing some information from these other global functions. But for right now, I know that we need both mass. What was the other thing that I missed there? Let's see. Mass of the black hole, mass of the object, and the length of the object. All right. So let's say mass underscore black hole, mass underscore object, and then some length of object. All right. And then for the tidal acceleration, it's pretty much going to be the exact same thing, minus the mass of the object. All right. And so we have a new constant here, right? If I factor out the m for tidal force, I can factor out m object mass divided by the black hole mass squared, and we get a negative. All right. So we're going to have a constant. Let's go back. And again, I'm going to just copy and paste a few things to make this simpler. So the speed of light, we're at SI units, so meters per second. We have our gravitational constant. And the overall constant is not going to be this anymore. We'll keep the negative sign, even though it's not needed as far as if we're only concerned with the magnitude. Yeah, we're only concerned with the magnitude. I'm going to keep the negative sign off. So the new constant is going to be a... And I need to be able to look at this one more time. C to the 6 over 4gm quantity, that quantity squared, or 2gm that quantity squared. Okay. Let's remember that. This is going to be a, say, pow, c to the 6th power. This is going to be divided by, I think it was a 4 times g times g. Because I'm factoring out the m because that's a parameter. All right. I think this is good. 6 to the 6th power divided by 4g squared. That's the constant that we're going to be dealing with both of these functions we're generating. Let me look at the comments really fast. I'm pretty sure I probably missed some stuff here. Yes, we are definitely working the effect out of the event horizon. So let me make sure that you can see the first scene. And so I made a substitution in for the R. So for this, I wonder, you can't see that actually. I'll highlight it. So I made a substitution in for this R that corresponds to this the Schwarzschild radius. So yeah, we're working on at the event horizon. All right. Good assumption, Michael. All right, let me quickly finish off this equation, and then I'm going to answer your question, Larry. All right. and I can quickly answer that last question though. So, if I'm not mistaken, these formulas should work. Well, yeah, this formula is a result from relativity. That is the Schwarzschild radius is a result from relativity. And the equation for the tidal force is also going to be true. All right. So let me go ahead and finish modifying this equation. So I think this is good so far for the constant. 2 to the 6th power times 4. Perfect. And lastly, we're going to end up returning the constant times, and for the tidal force, it was going to be, let me scroll down here, the mass of the object times the length divided by the mass of the black hole squared. Okay. So mass of object, I think it was times the length of object. It's weird that I put that as a lowercase l. I'm gonna be consistent there. All right, divided by the mass of the black hole squared times itself. And I think that that's good. And so I'm just going to simply copy and paste everything that I have here for the tidal acceleration function. Except now I'm going to remove the mass of the object in our final equation there. So I think this should be good. And so we have to note that our masses that we're submitting to the to this program, that the masses have to be in units of kilograms, and that the lengths have to be in units of meters. Okay. All right, I'm going to save this, and I'm going to go ahead and compile it. And so let's go here, the middle tab. I think I'm already in the correct directory. All right, we can compile. Oh no! Oh right, right. That's right. I have to change this as well. I wanted it to be a capital L. So I'll clear that, and I'll recompile, and it should be okay. All right. So everything's compiled correctly. Let's go ahead and scroll back up top. And let's now declare the functions within the main function. So I'm just going to copy this. And I will declare them here so that our main function is aware of our new functions that we've written out. And so output results to screen. All right. I now want to be able to submit more arguments. It's going to be a little weird how these arguments are for different things, but it's cool. It's cool. It'll still work out. So the new arguments that I have to submit would be, let's go ahead and do this. Let me scroll up and make some new variables. And actually, it just makes it easier for me to just do this. This is going to be the mass of the black hole, mass of object, and the length of the object. Alright. So with that in mind, of course, my parameters have increased. In total, I should need 3 more parameters added on. I have 2, 3. I think it should be 6 for this. Alright. And so I'm going to go ahead and retrieve those parameters. Or set the program up to take the user input. Let's put them here. And basically I'm going to have something along the lines of this. Where now this is going to be the third arc, or the 3, 4, and 5. Alright. I think this is good so far. Let's go ahead now and calculate. And so I'll go ahead and make a new statement. Given a black hole mass of this. Sorry guys, I know I'm having like these pauses, but I'm trying to make sure that I'm doing this correctly. SI units. Yes, gotta love SI units. I only have 5 arguments to the program. So yeah, 3. So you're right. I have 5 arguments, but the program name, it counts as an argument, if that makes sense. So with that check, it also includes argc counts up all of the I guess all of the parameters, including the program name that I'm executing. If it's wrong, it'll quickly not do anything for me, and I'll just reduce the number. But yeah, good. Thank you for looking out for that. Given a black hole mass of that. All right, and what is the other one? An object, or yeah, object mass of this. And I should make sure I also include the So I think with arc. So with this variable argc, I think it counts all of the individual strings that are being used to execute the program. Where the 0th string, or the first string, is the name of the program itself. So I have 5 arguments plus the name of. Okay, Barut, is that right? But yeah, let me get through this actually. I'm seeing it's 12:46 right now, and I want to just quickly write this out. So the mass of the black hole again has to be in units of kilograms, where it's blank kilograms. I'll do that actually, and if I'm not mistaken, that should give the name of the program. Let's see. Kilograms and object mass of that, kilograms and object length. And this has to be in units of meters. But yeah, Michael, thank you for keeping me honest here, because like I said, I make mistakes at times. I want to cut those down to a minimum. All right, so the mass is good, mass in kilograms, and object mass of that in kilograms, and object length in that of meters. So I can just get rid of that and just put meters. So then we're going to end up getting a tidal force of, and then we need to calculate our tidal force. So we're going to need two more. We're actually going to need two more variables, and so I'm just going to put them here. This is going to be our tidal force, and this is going to be our tidal acceleration. So I'll copy and paste these down below. And then I need to, of course, call the functions. Let's see. Where is it? Where is it? There we go. Ooh, that might not be good. Let me do this. I got the variable name, the same thing. Let's just do this. Let's say TF for tidal force and TA for tidal acceleration. All right. All right, and then that's -1. And if I'm remembering correctly, I think that the order was mass of the black hole,